Hello and welcome students to EPG Parsala of UGC. I am Divyakant Seth, Assistant Professor of the Department of Food Engineering and Technology, Tezpur Central University, Assam. In this module, we are going to discuss about fundamentals of fluid flow theory in paper Unit Operations in Food Processing. If you go to any food processing plants, you must have seen the plant operators, they handle different liquid foods, also the waters. They transport the liquid from one tank to a processing plant section. So they store it somewhere else in a tank. Also they use different measuring devices, the velocity of the flow, this kind of thing they will do. So as a food technologist, you must have some knowledge about the different properties of the food materials you are handling. Also, you must have the knowledge of this so that you can select a proper kind of machine like any food transporting pumps in the plant. So, seeing the importance of this fluid flow in this subject, we are going to discuss about the fluid flow and their behaviors in this module. In this module, we will learn about the static behavior of the fluid flow. Mainly, we will concentrate on the pressure measurement, how to calculate the pressure by using different manometers. Firstly, we will discuss about that. Also, we will do some numericals on that. Then we will go to the kinematics of the fluid flow. There we will visualize the flow patterns and the flow types. We will discuss about the different flow types so that you can utilize it in our different calculations. Then we will move forward to the dynamics of the fluid. Dynamics of the fluid means when the fluid is in motion, so we will calculate different properties of the fluid in motion. So there we will concentrate on the pressure drop in the pipe flow. Also we will discuss about different frictional losses in the pipe. Also we will discuss about different fluid measuring devices like rotameter, like venturimeter and orifice meters. Also we will discuss about the principle of all the equipments. Let us discuss about the importance of fluid flow in food processing. If you go to any food processing plant, you will observe that most of the foods are in liquid form. Say for example, liquid milk products. So, in handling those products, we have to have a very thorough knowledge about the properties of the fluid and its flow behavior. So that's why this module is very much important to know that different behaviors are well understood by you. Study of the fluid behavior is very important. Then, after knowing the behavior of the fluid, you will be able to understand how to handle those liquids or fluids, liquid handling, which is very much important because you are storing the liquid in one container or one vessel and you are transporting it to some other places in the plant. So, for handling, you need to, so liquid handling is a very important aspect in the liquid product processing plants. For handling of the liquids, that means transportation of liquid from one place to other, you require some pipelines, you require some pumps. So, depending on the behavior of the liquid or fluid, we have to select a proper size of pump so that it will drift the liquid from one place to other place. At the same time, you have to design the pipeline in such a way that there won't be any obstruction of the pipeline during the transportation of the fluids. Also, you need to take care about the hygiene of the pipeline, because if you have some dead ends, so what happens is some foulings may occur. So these kind of things you need to take care when designing the pipeline. So this is possible only when you will have a thorough knowledge about the behavior of the fluid, whether it is in motion or in static position. And the lastly, according to the fluid behavior, you could be able to, or you should be able to select the process equipments. Say for example, suppose you are using plate heat exchanger for heating of milk. You have a specific design for equipments, or you have a specific design for the heat exchanger for heating of milk. The same heat exchanger cannot be utilized for heating a chocolate mix. So these kind of selections of equipments you will only be able to decide only when you will have a knowledge of the fluid behavior and fluid properties. Students, let us learn about the science of fluid flow. The engineering sciences that deal with the flow of fluid is called fluid mechanics. The fluid mechanics involves the study of different properties of the fluids like the specific gravity, density, viscosity, etc. Also, it deals with the different forces involved in the mass and energy transfer of the fluid. Also, we will study here in this fluid mechanics the different patterns and different types of fluid flow. The different patterns I am talking about here is the streamline flow, strict line flow, timeline. We will discuss in detail in the subsequent slides. Also, different types of fluids like the uniform flow, non-uniform flow, steady state flow, unsteady state flow, one dimensional flow, two dimensional flows, three dimensional flows. So, this all we will study in the subsequent slides. Let us talk about the different branches or different categories of fluid mechanics. Broadly, they are categorized into three things. The first one is your fluid kinematics. The fluid kinematics is the study of the fluid flow when it is in rest. So, in this branch of fluid statics, we will mainly concentrate on the pressure. Pressure is nothing but force exerted by some unit mass due to its mass and gravity on a surface. The surface may be a plane surface or it may be curved surface. We will do lot of numericals on that. Later on, the next branch of the fluid mechanics we will study is the fluid kinematics. In the fluid kinematics, we will mainly concentrate on the flow of the fluid without concerning about the causes of the flow. Okay. So, here we will study about different patterns of the fluid flow and different types of the fluid flow as I have told you earlier. And the last branch of the fluid mechanics is the fluid dynamics. The fluid dynamics, it involves the calculation of different properties of the fluid when it is in motion. Also, the causes of the motion, the forces involved in causing the motion. So, there we will discuss about the Bernoulli's theorem. Also, we will do some numerical on that. So, in this slide, we came to know that the fluid mechanics is a broad branch where it is categorized into three branches of fluid statics, fluid kinematics and fluid dynamics. In the subsequent slides, we will discuss in detail about all the three branches. In the previous section, we have discussed about different branches of fluid mechanics. There, we discussed about the fluid statics. Fluid statics means the fluid statics means the measurement of different properties of the fluid which is at rest. So, one of the static property of the fluid is the pressure. Pressure is nothing but the force exerted by the mass per unit area. So, this is very important in designing of processing silo, storage tanks and so many other equipments. So, in day-to-day life, it is a very common practice to measure the pressure of any fluid which is flowing or which is in static. To measure those fluids, we are using some equipments. Most of the common devices which you use for pressure measurement are the manometers. Among the manometers, there are piezometer, simple U-tube manometers and differential manometers. Also, we use mechanical gauges like Bourdon's gauge and diaphragm. Manometers are the devices that measure the pressure of fluid at a point which is equal to the mass of standing fluid above it. That is, P is equal to gamma into H. So, the pressure measuring devices using this principle to measure pressure are called manometers. The top end of the manometer is open to atmosphere. The pressure in the fluid body is measured in terms of rise in height of fluid inside the tube. U-tube manometer use a different fluid as manometric fluid. Normally, mercury is used as manometric fluid. Why that is so? Because the density is too high, which is almost 13,600 kg per meter cube. So, huge pressure can be measured with a small displacement of manometric height. See the left side of the picture. Pressure at point A needs to be measured. So, take a reference line at 2, 3. Liquid column above left limb must be balanced with the liquid above the right limb. So, PA plus gamma 1 H1 minus gamma 2 H2 should be equal to 0. Or on the other hand, I can say PA is equal to gamma 2 H2 minus gamma 1 H1. The right hand side picture is a differential manometer. Here, the pressure difference between the 2 points is measured, that is at point A and point B. The pressure expression in this picture will be like this. Take a reference line as we did in the previous one. In the left limb, your pressure and the right limb pressure must be same. So, PA plus gamma 1 H1 minus gamma 2 H2 minus gamma 3 H3 is equal to PB. If we take PB into the left side, it will be PA minus PB is equal to gamma 2 H2 plus gamma 3 H3 minus gamma 1 H1. That PA minus PB is nothing but the pressure difference at the 2 points. The expression of pressure balance in this picture will be like this as we studied. Other types of pressure measuring devices are Bourdon's tube and diaphragm. They are spring loaded generally. The pressure energy of liquid is converted to mechanical energy in spring and the attached to it is deflected. Pressure is measured with a standard reference line. Based on the reference line, the pressure is either absolute or gauge or vacuum. If the pressure is measured from absolute vacuum as datum line, the pressure is called as absolute pressure. The violet color arrows indicate absolute pressure in this picture. Bourdon tube pressure gauge measures absolute pressure. Absolute pressure is equal to 101.325 kilopascal, which is also called as atmospheric pressure. The pressure measured above this atmospheric pressure, the datum is called gauge pressure. That means any pressure measured above the atmospheric pressure is called gauge pressure. Say for example, a Bourdon tube measuring 200 kilopascal absolute pressure is equivalent to 200 minus 101, that is 99 kilopascal gauge pressure. So, the relation between the absolute atmospheric and gauge pressure is developed as P absolute is equal to P atmospheric plus P gauge. That means P gauge is always above the P absolute. In many drying operations, you must have heard about vacuum pressure, where the pressure is maintained in vacuum for efficient and fast drying of food products. The vacuum pressure is the absolute pressure in short of atmospheric pressure. If any pressure falls below the atmospheric pressure, that is 101.325 kilopascal, the shortage is said to be vacuum pressure. Suppose the absolute pressure is 55 kilopascal. This is less than the atmospheric pressure. The vacuum pressure thus will be 101 minus 55 is equal to 46 kilopascal. That means we can say 46 kilopascal of vacuum is maintained. The relation is thus P vacuum is equal to P atmospheric minus of P absolute. Manometers are used to measure both gauge and vacuum pressures. After having a brief introduction on fluid statics, now we will come to fluid kinematics, which is a very vital component of fluid mechanics because you have to visualize the flow in this case. Fluid kinematics is a branch of fluid mechanics which describes the fluid motion and its consequences without considering the causes of fluid motion. Here, we shall study about the fluid velocity in a fluid field. The fluid flow patterns and types of flow are the two important aspects to be discussed. Pattern means orientation of fluid particles in both time and space. It is completely a visual subject. The common fluid patterns are streamline, pathline, streak line, and timeline. Streamline is an imaginary line drawn in such a way that the tangent to this line at any point represents the local velocity at that point. Understood? Again I repeat, the streamline is an imaginary line drawn in such a way that the tangent to this line at any point represents the local velocity at that point. You can see this in this picture which is there in the left side. It represents the contour of velocity field at an instant. The path line is the actual path traveled by a fluid particle at different instances. You can see it at the middle that the path line is drawn. That means this is the actual path traveled by a particular fluid at different instances. Streak line is the line joined by particles which have traveled through a common point or locus. When a set of points form a line at different instants, it is called timeline. Streamline and timeline give the flow pattern at an instant, whereas strict line and path line represent the pattern with a time duration associated with them. I hope you can differentiate between streamline, strict line, path line and timeline. Now we'll discuss about the different types of flow. Among the types of flows, these are steady state flow, unsteady state flow, uniform flow, non-uniform flow, compressible flow, laminar flow, turbulent flow, transient flow, 1, 2 and 3 dimensional flows, rotational flows and irrotational flows. So in this section, I will discuss one by one what is steady state flow, what is a steady state flow and so on. Steady state flow is the type of flow where the fluid properties at any point does not change with time. That means the partial derivative of the fluid property with respect to time is equal to 0. Here we have shown del V by del T with respect to the space xyz is equal to 0. Or also you can write del rho by del T with respect to xyz is equal to 0. That V and rho are the fluid properties. So the properties of the fluid with respect to time at any point does not change. So this is called the steady state flow. Unsteady state flow is the reverse of the steady state. That is, the fluid properties like V, velocity and your density changes with time at any point. That is, del V by del T with respect to space is not equal to 0 and del rho by del T with respect to the space is not equal to 0. Now come to uniform flow. At a space, at a particular space, does not change with time. Uniform flow is the type of flow in which the velocity and the other flow parameters at any instant of time do not change with respect to space. That means the magnitude and direction of velocity vector are constant in uniform flow. That is represented as del V by del S with respect to time is equal to 0, where S is the space here. In the non-uniform flow, del V by del S with respect to time is not equal to 0. That means the fluid properties changes with respect to time. So this is called non-uniform flow. Now, what is compressible flow? Compressible flow means, as a layman, you can say that the fluid which can be compressed is called compressible flow. That means the density changes with time or space. But in most of the practical cases or practical applications or practical calculations, we assume that the fluid is incompressible. Now come to laminar flow. The laminar flow, a set of points flow through a well-defined path or streamline. That is laminar flow. When the fluid particles pass through a well-defined path or streamline, they are called laminar flow. That means there are no such turbulence which is occurring in the flow. The reverse one is your turbulent flow. The turbulent flow, the fluid particles move randomly. That means they change the direction in every instant. The flow of laminar and turbulent is characterized by a dimensionless number, that is Reynold's number, which is the ratio of inertial force to viscous force. Now coming to 1, 2 and 3-dimensional flows. The flow is called one-dimensional when the velocity or any fluid is flowing at a single direction. In a space, you have three directions. If the fluid is flowing in a single direction or the velocity component of a single direction is taken care of, that is called one-dimensional flow. So it is represented as V is equal to Ui, that is the velocity component in x direction is taken care here. Two-dimensional means the velocity with two components in x and y direction, that is u and v. So v is equal to ui plus vj. Likewise, the three-dimensional flow is represented as v is equal to ui plus vj plus wk. So they are three-dimensional. This is only the visualization of the flows, because the fluid flow has always three dimensions, but for our calculation purpose, how much of dimension will take, that depends on our situations. Now coming to rotational flows. Fluid flows in a streamline and it rotates about its own axis. When the fluid flows in a streamline and it rotates about its own axis, then we call it as rotational flow. When the fluid does not rotate about its own axis, we call it as irrotational flow. Let us discuss about Reynolds number. A fluid mass moves from one place to other due to the forces of momentum. At the same time, one resisting force acts against the flow, which is due to the viscous force of the fluid. So, changes in the flow characteristics occur if the internal force surpasses the viscous force. From this understanding, one unitless number has been derived by Dr. Reynold. Reynolds number is the ratio of inertial force to viscous force. Inertial force is dependent on the density of the fluid, fluid velocity, and dimension of pipe through which it flows. The inertial force is represented as rho a v square. The viscous force, that is the shear stress, is a product of viscosity and velocity gradient. The gradient is dv by dy per unit area. So, the expression of Reynolds number will be rho Lv divided by mu. In case of pipe flow, the characteristic length is replaced by the diameter. So, it is represented as rho dv by mu. Reynolds number can also be expressed in terms of mass flow rate. Mass flow rate, if discharge multiplied by density, we call it as mass flow rate. Hence, Reynolds number is equal to 4m divided by pi d mu. Reynolds number helps in quantitatively describing the flow characteristics of fluid in a pipe. When the viscous force is high compared to inertial force, the flow will be low. The flow is said to be in a laminar region as long as the Reynolds number reaches 2100. Since viscous force predominates, the flow is otherwise called as viscous force. That means the laminar flow is also called as viscous force. The Reynolds number in between 2100 to 4000 signifies transitional flow. Reynolds number greater than 4000 indicate little influence of viscous force on the flow characteristics. This is called turbulent flow. Laminar flow is always in a streamline pattern. since the fluid layers are not disturbed by the drag force and the velocity profile remains same in a layer, which is not happening in turbulent region. Let us take an observation of day-to-day life. You must have noticed your grandpa watering in a garden through a pipe. If you squeeze the end of the pipe, the water is sprayed with high velocity. That is what your grandpa used to do when he wishes to water the farther distant trees. So what happens here? The kinetic energy increases and the water is spread to further distance. This can be proved with the principle of conservation of mass, which is very common in fluid mechanics, and we can derive this equation, and very popularly it is known as equation of continuity. As per the law of mass conservation, the mass entering to a system must be equal to the mass leaving the system, with an assumption that there is no accumulation or loss. Let us consider a pipe whose diameter at both the ends are different. As we see in this picture, the pipe at the left side has a diameter of D1 or area A1, and pipe at the right side has a area of A2. The velocity profile in these two ends will also be different. Suppose the velocity at the left hand side is V1 and the right hand side is V2. The mass flow rate is the product of density, cross-sectional area and velocity. According to the conservation law, the mass flow into the pipe through the left side must be equal to mass coming out from the pipe from the right hand side. That means M1 must be equal to M2. And what is that M1? M1 is nothing but rho 1 A1 B1, and M2 is nothing but rho 2 A2 B2. So rho 1 A1 B1 must be equal to rho 2 A2 B2 according to the conservation law. Let us assume that the fluid which is flowing through the pipe is incompressible. When it becomes incompressible, the density does not changes. So rho 1 must be equal to rho 2. So you can eliminate this rho 1 and rho 2 from this equation. So it will be now become A1 V1 equal to A2 V2. Or you can say that V is inversely proportional to A. That means when the area increases, velocity decreases, and when the area decreases, velocity increases. That's what you observed when your grandpa was watering the plants. He was reducing the area. So while reducing the area, the velocity was increased. That's why the water was spread to a further distance. The product of area and velocity develops a new term called discharge, whose unit is meter cube per second. That means A1 B1 is nothing but Q, that is discharge in meter cube per second. So Q1 is equal to Q2. Discharge in is equal to discharge out. That is mass flow in is equal to mass flow out. I hope it is clear to you. Now come to the fluid dynamics, the third category of fluid mechanics. The fluid dynamics deal with the study of flow and the energy involved in causing the flow. The principle of conservation of energy is the energy is neither created nor destroyed, and the total energy within a system remain same. That means different kind of energies, mostly these are potential energy, kinetic energy and pressure energy. That means the major three energies at any point remain constant in a system. Bernoulli's equation which is a consequence of conservation of energy, is applied to an ideal fluid mass in a flow field. Bernoulli's equation states that the sum of pressure energy, potential energy and kinetic energy remains same at all points along a straight line. I repeat, Bernoulli's equation states that the sum of the pressure energy, potential energy and kinetic energy remains same at all along the streamline. To derive this equation, we need to assume that the fluid is ideal. That means viscosity is 0. The fluid must be incompressible. The fluid must be incompressible in nature. A streamlined flow pattern has to be there with a steady state flow, and flow should be in a laminar region. With these assumptions, now we will proceed like this. If we consider a column of fluid of height h, the total force applied will be rho AGH. The pressure capital F by A can be represented in terms of the head small h, which is equal to P by rho G. Kinetic energy is always associated with the movement of fluid mass. So the kinetic energy can be best described by the velocity of fluid. The energy head thus is represented as V square by 2G. If we consider 2 points as shown in figure, then we derive that, or we say that H1 plus P1 by rho G plus V1 square by 2G must be equal to S2 plus P2 by rho G plus V2 square by 2G. The application of Bernoulli's equation is enormous, particularly in fluid flow in food processing. It is very much helpful in pipeline design and selection of pumps. Also, it is very helpful in designing or describing the principle of the fluid flow devices. With the understanding of the Bernoulli's theorem, now let us solve a numerical based on this Bernoulli's theorem. Milk is flowing at a rate of 1500 liters per hour through a pipe of diameter 10 cm at a pressure of 80 kilopascal. The pipe is reduced to 7 cm diameter at the other end. Neglecting the frictional losses in pipe and the velocity of fluid, find out the pressure built up at the end of the pipe. Assume milk density as 1030 kg per meter cube. So to solve this, now first we will draw a diagram. The left side, the diameter is 10 cm and the right side, the diameter of the pipe is 7 cm. The pressure at the left side is 80 kilopascal and your flow is, or the discharge is 1500 liters per hour. It is asked that when the pipe is reduced to 7 cm diameter in the right side, what should be our pressure? Let us first convert this liter per hour into meter cube per second, that is in SI unit. So 1500 liter per hour is equal to 1500 into 10 to the minus 3 divided by 3600 meter cube per second, which is equal to 4.17 into 10 to the minus 4 meter cube per second. Given the diameter, first you need to calculate what is the area. So area in the left hand side will be equal to A1 is equal to pi by 4 d square, that is pi by 4 into 0.1 square, which is equal to 7.85 into 10 to the minus 3 meter square. Likewise, you can calculate A2 as pi by 4 into 0.05 square, which is equal to 2.5 into 10 to the minus 3 meter square. You have the discharge at the left hand side, you have the area
in the left hand side. So you can calculate the velocity at the left hand side. This can be calculated as V1 equal to 4.17 into 10 to the minus 4 meter cube per second divided by 7.85 into 10 to the minus 3 meter square. So that becomes 0.053 meter per second. That is the velocity at the left hand side. That means velocity at bigger diameter pipe section. Same way you can calculate the V2 at the right hand side. The V2 becomes 0.167 meter per second. Now apply Bernoulli's equation. The Bernoulli's equation says that all the head, that is the pressure head, kinetic head and elevation head, the summation of all these three at any point will be same. So it will be Z1 plus P1 by rho g plus B1 square by 2g is equal to Z2 plus P2 by rho g plus V2 square by 2g. Assuming that there is no elevation of the pipe, we can neglect Z1 and Z2. So our final equation will be P1 by rho g plus B1 square by 2g is equal to P2 by rho g plus V2 square by 2g. We can rewrite this in this form: P2 equal to P1 plus rho by 2 into V1 square minus V2 square. Now putting the values of rho and V1, V2 in this equation and P1 of the left side diagram, you can calculate P2 equal to 80 plus 1030 divided by 2 into 0.053 to the power 2 minus 0.167 to the power 2. Then we will get the pressure P2 is equal to 79.98 kilopascal. So what we observed here in this numerical is, initially your pressure was 80 kilopascal at the left hand side. When you reduce the diameter to 5 centimeter, your pressure was reduced. The loss of pressure head is compensated by the increase in kinetic energy.
Students, now we will discuss about the energy losses in pipe. It is a very common practice to select a proper size of pump as per the requirement of the drift and the distance it would travel. If we are not able to select a proper size of pump, it cannot transport our fluid of concern to our required distance. That is why we need to select a proper size of pump. So what is importance in this slide? Let me tell you. Because there are some losses, the energy which we are inputting in terms of the mechanical energy is not getting transmitted to the fluid. In this, we will discuss about different losses due to friction. One of the major losses in the pipe flow is due to the viscosity of the fluid. That means, more the viscous the product is or the liquid is, more resistance it is offered. Okay. So if we are handling a viscous fluid like chocolate mix, we need to select a higher HP motor for transporting the chocolate mix from one place to other place. Whereas if you are handling a water, some water, then you may not require that amount of horsepower in transporting the water to the same distance. So fluid viscosity is one of the major losses. There are some other minor losses, although they are not so significant. The minor losses includes the losses due to sudden enlargement of the pipe, the losses due to sudden contraction of the pipe. Also, if you have some pipe fittings, it is inevitable that there are some pipe fittings in your pipe lines. So because of that pipe fittings, there may be some losses. Also, in some cases, we see that if there are some obstructions, in the obstructions, if there are some obstructions, then there will be some small losses of energy. But overall, these losses are very insignificant. That means we can exclude those losses. So the major concern of our losses will be the major loss, that is the loss due to friction, and that is due to the viscosity of the fluid. The major loss also occur due to the roughness of the pipe. More the rough surface of the pipe is, the more the obstruction it causes at the interface between the pipe surface and the fluid surface.
In the previous slide we have discussed, I gave a general overview of the different kind of losses. One of the major losses is your frictional losses. Let us discuss about the loss due to pipe friction, which is a very major loss in the pipe flow. Assuming horizontal pipe and a constant velocity flow, we can write the Bernoulli's theorem. We can write the Bernoulli's equation in this way: H1 plus P1 by rho g plus B1 square by 2g is equal to H2 plus P2 by rho g plus B2 square by 2g plus Hf. So here Hf is the loss of head due to pipe friction. Assuming there is no elevation head and no velocity head, so we say that the loss of head due to friction Hf is equal to P1 minus P2 by rho g. Darcy-Weisbach developed an equation considering the relationship of loss to the dimensions of the pipe. The dimensions are the length of pipe and the weighted perimeter of pipe. In calculation, hydraulic diameter was used, which is equal to 4 times area to weighted perimeter. They developed a proportionality constant called friction factor, which is denoted as small f, and is equal to the drag force per unit area divided by the density and kinetic energy. The drag force minus dp by dx will be now is equal to f rho v square by 2d, or you can write P1 minus P2 is equal to Fl rho v square by 2d. So combining equation 1 and 2, we obtain the combining equation 1 and 2 will obtain Hf is equal to F into L by D into V square by 2g. This is equation, or this equation is popularly known as Darcy-Weisbach equation of friction loss through pipe. Let us discuss about the Fanning's friction factor and Moody's diagram. Darcy-Weisbach equation can also be represented as Hf equal to 4f dash L by D into V square by 2g, where f dash is called coefficient of friction or Fanning's friction factor. D here is in this equation is the diameter of pipe, which was hydraulic diameter in previous equation. Fanning's friction factor is a function of Reynolds number and the relative roughness of pipe. In the laminar region, that is NRE, Reynolds number less than 2100, the relation can be given as f dash is equal to 16 by Reynolds number, 16 by NRE. Reynolds number varying from 4000 to 10,000, the empirical relation developed is f dash is equal to 0.079 divided by Reynolds number to the power 0.25. In the complete turbulent region, some other relation is also there. The graph showing the relationship of Fanning's friction factor with Reynolds number and relative roughness is called Moody's diagram. That means in calculation we will take the help of this Moody's diagram to calculate the friction factor at different roughness of pipe at particular velocity of flow, that is in the form of Reynolds number. The roughness of pipe can also be found from literature for different materials, like roughness is less in case of stainless steel compared to plastic or wood. After calculating the nature of flow, that is calculating the Reynolds number, Moody's diagram is used to calculate the friction factor for head loss calculation. I hope you understood the utilization of Moody's diagram. I repeat, Moody's diagram is utilized to calculate the friction factor at different roughness of pipes at different Reynolds number. You can take the help of this empirical relationship after calculating the Reynolds number. If it is in the laminar region, you take the first case, that is F dash is equal to 16 by Reynolds number. If it is in the turbulent region, then you can take the help of the second case, that is F dash is equal to 0.079 divided by Reynolds number to the power 2 pi. After having a discussion on the major loss, that is friction loss in the pipe, let us give some light to the minor losses. Though their loss is not so significant, we need to know what are those losses and how you can calculate those losses. The expression of minor losses can also be derived from the Bernoulli's equation. If you want, you can refer any standard books, so you can see the derivation of the minor losses. So we won't go in detail of the derivations here. Let us discuss only the expressions of head losses. First, take the case of sudden enlargement, the loss due to sudden enlargement. If a pipe is enlarged at a point, the velocity gradient occurs, and so head loss is encountered, which is equal to He is equal to V1 minus V2 whole to the power square divided by 2G. Likewise, when the pipe is contracted to smaller diameter, as in the case of orifice meter, the loss will be expressed as Hc is equal to K into V2 square by 2G, where the K is expressed as 1 by Cc minus 1 whole to the power 2. Here, Cc is called coefficient of contraction. The value of K varies from 0.5 to 0.7. Now, coming to the loss due to bend in pipe. The bend in the pipe cannot be avoided in pipeline design. Since the velocity is a vector quantity, the change in the flow direction changes the flow velocity, so some loss occurs, which is equal to Hb is equal to K V square by 2G. K here is bending coefficient. The fittings like pressure gauge, thermocouple, etc. in the pipeline disturb the normal flow region. The loss of height will be, in this case, is K into V square by 2G, where K is the coefficient of pipe fittings. The flow regime at the entrance and exit also are different from the fully developed regime. The loss at the entrance of the pipe is equal to the loss due to entrance will be equal to Hi is equal to 0.5 into V square by 2G. At the same time, the loss at the exit will be Ho is equal to V square by 2G. So, all the losses are summed up to calculate the total head loss in pipe flow. That is, the losses we discussed here and the frictional losses. So, in combination of all these three, all these we will get the total head loss in the pipe. So, considering these losses, we can calculate our required pressure so that we can select a proper pumping system for our pipeline. Now, let us discuss about some flow measuring devices. One of the major applications of Bernoulli's equation is the design of flow measuring devices. Flow measuring devices are used to measure the flow rate of fluid. The common devices used to measure the flow rate, or we can call it discharge, are venturimeter, orifice meter, pitot tube and flow meter. Venturimeter consists of a converging section, a throat section and a diverging section. An U-tube manometer is attached at 2 points, that is one limb before the entrance and the other limb is attached at the throat. When fluid flows, the area becomes constricted, thus the velocity increases. That means kinetic energy increases. But as per the Bernoulli's theorem, the total energy at all points remains identical. So increase in kinetic energy is compensated by reduction in pressure energy, assuming elevation head has assuming elevation head as 0. With this understanding, the pressure energy in terms of manometric head is derived from the main equation. The equation is Q actual is equal to CD into A1 A2 divided by A1 square minus A2 square whole root over into root over of 2GH, where CD is called coefficient of discharge whose value is less than 1 always. By multiplying the CD value with the theoretical discharge, we can get the actual discharge. Got it? How to calculate the discharge with the help of this venturimeter? For this, you need to have the area A1 and A2 with you and the head difference, that is in terms of H, so that you can calculate the discharge Q. Now come to the next device, that is orifice meter. Orifice meter also works with the same principle, but the design of this device is different. Orifice meter is a flat metal plate on which a circular hole is made. This plate is attached along the cross section of pipe, so fluid flows through the narrow circular section. Since the flow field suddenly changes, maximum loss of energy occurs. That means the value of theoretical discharge and actual discharge differs significantly. In other words, coefficient of discharge is less compared to venturimeter. That is the reason why, for more precision measurement and large volume handling, venturimeter is mostly used. Of course, the design is difficult and hence cost is also high. Pitot tube is basically a glass tube bent at 90-degree angle, and the lower portion, which is open mouth, is faced upstream. It is based on the principle that if the velocity of flow at a point decreases, the pressure head increases, since the kinetic energy is converted to potential energy. Due to the pressure, the fluid rises in the tube. Coming to rotameter, rotameter is also called as variable area meter because the area is changing at different sections. A fluid is allowed to pass through a tapered tube whose constriction is constant. As the fluid moves downward, the area of flow decreases. Thus, the velocity increases. The pressure gradually decreases. The rate of pressure drop is a function of flow rate in this case. So, in a nutshell, we have discussed about the principles of the flow measuring devices. I hope you understood the principles of flow measuring devices.
Students, let us summarize what we have learned in this module. First, we discuss about the different branches of fluid mechanics, that is the fluid statics, fluid kinematics and fluid dynamics. Also, we discuss in detail about all the three branches. In the fluid statics, we calculated different pressure by using manometers. I hope you will be able to do any kind of numericals related to pressure calculation. Also, we studied about the visualization of the flow patterns and different types of flows. In the dynamics, we studied about the Bernoulli's theorem. We applied Bernoulli's theorem. Also, we calculated the different pressure drops. How to do that we studied, and we calculated different frictional losses in the pipe flow. There are different cases. We discussed about that in detail. I hope you will be able to calculate any kind of frictional losses through pipe flow. And lastly, we applied Bernoulli's theorem and we studied the principle of the measuring devices like rotometer, venturimeter, orifice meter, and we studied about the utilization of all the measuring devices in food processing plants. Thank you very much and have a good time.